can't deal with any more code today, so we are doing, no, it's this one. Get rid of that. Yeah. I just need to be able to chill. Let's see. How does, let's see. Try to start reading this. How does leader-based replication work under the hood? Several different replication methods are used in practice. So let's look at each one briefly. Statement-based replication. In the simplest case, the leader logs every write request statement. Okay, hold on. Let's do this first. And data models refers to human relevant information being stored in multiple places. SS tables are storage string tables backed by some in-memory data structure, and it helps. Once they get so large, they become segment files, and it helps because it helps to keep things sorted because merging and compaction. I should say compaction because it goes compaction then merging. Compaction and merging become easier, more straightforward. A message broker is an intermediary between a requester and a service. Acts like a queue or a buffer, and it desyncs the connection. Multiple consumers and receivers. Store queue. Okay, that was good. Compatibility. When it comes to encoding and decoding, two things are compatible if they can effectively communicate with each other. Yeah. These guys are sick. Code generation. Compression, better compression, smaller in size. A form of documentation. Let's go with that. More compact, form of documentation. I forgot this, but okay. Good enough. Service. Exposes an API through a server. Yeah. A client connects to a server. Nice. What are the pros and cons of JSON, XML, and CSV? Human readable. Widely used. And
Cons. Too ambiguous. No binary sequence. Binary numbers. Can't use binary numbers. No support for binary numbers. No schema. Okay, that was better. A server responds to a client, usually has a service running on it. The actor model. Oh man. Dude, today was rough. The actor model. Oh my god, dude, what? The actor model is a way of each actor has its own state. They can communicate with each other, but no message is guaranteed to arrive. Same thing. Each service is an actor. They communicate with each other. Replication is the same data set many times. Vertical scaling or scaling up is bigger and bigger machines. Still a single process. Horizontal scaling is many machines, multiple processes. Coordination is done at the software level. Failover is in a master or in a leader follower setup system. Leader follower replication. If the leader fails, it's how we designate a new leader, and what to do when the leader comes back online. In chapter 3, we discussed how storage engines represent data on disk, and we found that usually every write is appended to a log. In the case of a log-structured storage engine, this log is the main place for storage. Log segments are compacted and garbage collected in the background. In the case of a B tree, see B trees on page 79, which overwrites individual disk blocks. Every modification is written to a write-ahead log so that the index can be restored to a consistent state after crash. I still don't know what I read. I literally cannot focus. This is insane, dude. Ugh. Log segments are compacted and garbage collected in the background, okay? In case of B trees, which overwrites individual disk blocks, every modification is first written to a write-ahead log. So that, yeah. In either case, the log is an append-only sequence of bytes containing all writes to the database. We can use the exact same log to build a replica on another node. Besides writing the log to disk, the leader also sends it across the network to its followers. When the follower processes this log, it builds a copy of the exact same data structures as found on the leader. This method of replication is used in Postgres and Oracle, among others. The main disadvantages is that the log describes the data on a very low level. A wall contains details of which bytes were changed on which disk blocks. This makes replication closely coupled to the storage engine. If the database changes its storage format from one version to another, it's typically not possible to run a different version of the database software on the leader and the followers. That may seem like a minor implementation detail, but it can have a big operational impact if the replication protocol allows the follower to use a newer software version than the leader. You can perform a zero downtime upgrade of the database software by first upgrading the follower and then performing a failover to make one of the upgraded nodes the new leader. If the replication protocol does not allow this version mismatch, as is often the case with wall shipping, such upgrades require downtime. Is that what it was called? Logical row-based log replication. An alternative is to use different log formats for replication and for the storage engine, which allows the replication log to be decoupled from the storage engine internals. This kind of replication log is called a logical log to distinguish it from the storage engine and its physical data representation. Logical row-based. Okay, so we're just, yeah, okay. trigger-based replication. The replication approaches described so far are implemented by the database system without involving any application code. In many cases, that's what you want. Circumstances where more flexibility is needed. For example, if you want to only replicate a subset of the data, or you want to replicate from one kind of database to another, or you need conflict resolution logic. See handling write conflicts on page 171. Then you may need to move replication up to the application layer. Some tools such as Oracle Golden Gate can make data changes available to an application by reading the database log. An alternative is to use features that are available in many relational databases, triggers, and stored procedures. A trigger lets you register custom application code that is automatically executed when a data change, write transaction, occurs in a database system. The trigger has the opportunity to log this change into a separate table from which it can read by an external process. The external process can then apply any necessary application logic and replicate the data change to another system, data bus for Oracle, and Bucardo. Being able to tolerate node failures is just one reason for wanting replication. As mentioned in the introduction to part 2, other reasons are scalability, processing more requests than a single machine can handle, and latency, placing replicas geographically closer to users. Leader-based replication requires all writes go through a single node, but only queries can go to any replica. For workloads that consist of mostly reads and only a small percentage of writes, a common pattern on the web, there is an attractive option: create many followers and distribute the read queries across those followers. This removes load from the leader and allows read requests to be served by nearby replicas. In this read scaling architecture, you can increase the capacity for serving read-only requests simply by adding more followers. However, this approach only realistically works with asynchronous replication. If you tried to synchronously replicate to all followers, a single node failure or network outage would make the entire system unavailable for writing. And the more nodes you have, the likelier it is that one will be down. So a synchronous configuration would be very unreliable. Unfortunately, if an application reads from an asynchronous follower, it may see outdated information if the follower has fallen behind. This leads to apparent inconsistencies in the database. If you run the same query on the leader and the follower at the same time, you may get different results because not all writes have been reflected in the follower. This inconsistency is just a temporary state. If you stop writing to the database and wait a while, the followers will eventually catch up and become consistent with the leader. For that reason, this effect is known as eventual consistency. The term eventually is deliberately vague. In general, there is no limit to how far a replica can fall behind. In normal operation, the delay between a write happening on the leader and being reflected on a follower